Hi guys, so here's where we're going to be heading to next. We've been doing derivatives, and we're going to do some applications now, and we're going to head into a topic called optimization. And optimization involves minimizing and maximizing. And if you think to what we've been doing, where we're looking for minimums and maximums, that should click off into your brains that we're talking about the first derivative test. So last year, you guys learned this, by the way. You guys were doing stuff where you, for example, as you're looking right here, this is literally out of a pre-calc textbook that I'm sure you guys used last year, is that you have a farmer wants to make a rectangular enclosure using a wall as one side and 120 meters of fencing for the other three sides. So you're a farmer, and you've got the wall of your barn, so that way you want to put your chickens in the coop or whatever, and you're like, ooh, chicky. So you want to basically use as much of that fencing to get as big of an area as you want to get. So in other words, our goal is to maximize the amount of area we could get out of 100 meters of fencing, okay? So here's a couple of things that I like to think about. I'm like, there is something called a primary equation, and where's my little thing here? We have a primary equation, and we have a secondary equation. And the great thing is that in the primary equation is what we're trying to minimize or maximize. The secondary equation is going to help us get to our destination. So the thing of it is, if this side is x, this side is also x, and we'll call his buddy over here y. And our goal is to maximize the area of this enclosure. And because it's shaped like a rectangle, you guys should all be saying to yourself, our primary equation is area is equal to x times y. So that's our primary equation is, I'm going to write it over here. I'm going to write the primary here is area is equal to x times y. So this right here is the primary that we're talking about. Now, if you look at it, unfortunately, the primary equation, the area is in terms of both x and y. So what we have to do is we have to come up with a secondary equation that's going to help us write either x or y out of the equation, because I want the area solely in terms of, look at this, the stupid light, in terms of one variable. So in my secondary equation, I'm going to go back to the question, and it's telling me I have 100 meters of fencing for the three sides. Now, if that means that I'm about 120 meters to put around this thing, then that's screaming to me that that's perimeter. So my secondary equation is going to be 120 is equal to, and if I do this, it's going to be 2x plus y. And I hope you guys figured that out, because x and x gives me 2x and a y. So now if you look at your secondary right here, which is beautiful, is I can solve for one of my variables. And I'm going to solve for y because it's easier. So now I know y is equal to 120 minus 2x. Now ask yourself, why did I do that? Because if you look back up in your area equation, your area is in terms of x and y, but now I can write y in terms of x. So the area function, which I can now write as a function of x, is equal to x times 120 minus 2x. Okay? So this right here is what I'm on the hunt for, finding out what's going to give me the maximum area that I can use with this 120 meters of fencing. So now I have this guy right over here, so I'm going to bring it on down. Wee-haw. Okay, and my area is equal to 120x minus, look at me, I'm writing on an angle, minus 2x squared. Now I'm trying to maximize this. So if I'm trying to maximize this, something should be alerting your brain that's saying, find the yes, the derivative. So if I take the derivative of this and set it equal to, good for you, 0, it's going to hook us up. So a prime of x is equal to 120 minus 4x, which I'm going to set equal to 0. And if I solve this equation for x, I can already see that my answer is going to equal 30. So x is equal to 30 is going to hook that up for me. Now I have to double check to see if x equals 30 is going to be my maximum. So I have to do my derivative test. So I have to do anything less than 30, like a prime of 10 here, and then maybe a prime of 100. Okay, boom. So I have to do my first derivative test to actually confirm that this is going to yield a maximum. So if I do a prime of 10, and if I plug 10 in here, I get 40. 120 minus 40 is a positive number. And then if I plug 100 in, because that's 100, that looks a little disheveled, but 120 minus 400 is clearly a negative number, so therefore I have shown that this is in fact a maximum. So now I know that since x is equal to 30, I can find out what y is equal to. So x is equal to 30. How do I get the y value? Look around, you guys, look around. That's right, over here you have in your secondary equation that y was equal to 120 minus 2x, so that means I can plug that in. So 120 minus 60 is 60. So what that tells us is that to maximize the amount of space that I have for the chickens, with 120 meters of fencing, it's going to be a 30 by 60 meter space. Okay, let's do another one. Why not, right? Let's do another one. All right, let me go on the hunt for what I'm looking for, and let me just do this real quick. Was it this one? Nope, that's the one we had. Here he is. Okay, so suppose you have 102 meters of fencing to make a two side-by-side enclosures as shown. What is the maximum area that you can enclose? So again, we have that 102 meters of fencing. This time, unfortunately, you have pigs and chickens and they can't live together. So we have to figure out what to do so that we can separate them with 102 meters of fencing, that we give as much space as we can to both the pigs and the chickens. Okay, all right. I hope you're laughing. It's a little insane, but that's what we do. Let me click onto this so that my workspace is actually up and moving here. So here's the thing. If you know that this is x, then you know that, whoops, I need to put this on my pen, that this is also x, and so is he, right? Now, you have two side-by-side rectangular enclosures. So here's what I'm going to do. I'm going to call this big guy right over here, I'm going to call him y, because I don't know what those two are going to be. So we want to maximize the amount of area that we can enclose, okay? So if you look over here, the entire area that we are enclosing is still going to be x times y. And again, what equation is that called, you guys? I hope you said the primary, because it's called the primary equation, because that's what we're trying to maximize. Now, we have 102 meters of fencing, so if we're going around the fence, don't forget we have to account for the guy right over here, that he's also going to be accounted for in the fencing. So that means then I have my perimeter equation, which is 102. So my perimeter is equal to 102. So if you want to pause and think about it, la 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 la, or hit pause right now and you come up with what that's going to equal, I'll wait for you. Well, I hope you came back and you're good to go, because here's what I'm thinking. This is also y right over here. So the perimeter equation is going to be 3x plus 2y. That's what I, in fact, got from that one. So with that said, we are going to go ahead and I'm going to solve for y. So if I solve for y, I get 102 minus 3x over 2 is equal to y. Because this right over here, remember, this is my secondary and this is my primary. So now the nice thing is with my primary equation, I can plug this guy right in here and in for y, so that my area is a function of x. So a of x is going to be equal to x times 102 minus 3x all over 2. So if I multiply this through, right, and I distribute, or if I divide this out here too, I'm going to do two things at once before I even move on here. Half of 102 is 51, like if I divide that, so I'm going to have a 51x minus a 3/2 x squared. So if you need a moment to go figure out what I did, because your algebraic skills leave a lot to be desired, I again will wait for you. So because if I divide this out, I get 51. If I divide this out, I get 3/2. If I multiply through by x, it leaves me with this. So now I want to maximize this, because again, we're looking for the maximum area that we can enclose right in here. Then my area is given by that. So if I want to maximize, I'm screaming derivative in my head. So the derivative of this is just 51 minus 3x. So set it equal to 0. So I have 51 minus 3x. And x is equal to 51 goes in 1, and then remainder of 2 is 17. So I got x is equal to 17. Now, again, I have to confirm that it's a maximum, so I have to do my first derivative test. So I'm going to pick something smaller than 17 but bigger than 0, because if x is 0, this whole thing collapses, so you got to pick something bigger. So let's be crazy and maybe even go with 1. And then a prime of 30, whatever, okay? So if I go to my derivative and I plug in 1 into my derivative, I get a positive answer. If I plug in 30, clearly it's negative, so I have just shown that it is in fact a maximum. So my x is equal to 17, so now I have to figure out what my area is going to be. So in order to do that, I have to find out what y is equal to. So I could take this right over here and go back into my secondary and plug my answer in for y. So I get 102 minus 3 times 17, and 3 times 17 is 51. So 102 minus 51 is 51, so I'm assuming it's 51 halves, right? I'm going to get my calculator because I'm so freaking lazy. That's a horrible sound, isn't it, on the dumbass desk? But anyway, oh, that one doesn't work. That's great. Oh, time keeps on ticking, ticking, ticking. So 102 minus 3 times 51, divide that by 2 is 25.5, okay? So y is equal to 25.5. So that area that yields the maximum times 17 is going to give me 433.5. So 433.5, what is it, square meters, is what my maximum area will be that will get us in this fence right over here, in that enclosure right there, okay? I'm going to shoot for another one. Hopefully I can squeeze another one in here, and if I can't, I can't. So hold on, let me cancel that first. I got to go with a new picture. So as I'm talking and looking up what I need to look up, because we're trying to remember. Is that it? Yes. Okay. I can start this, which is great. Remember, you have a primary, you have a secondary, and you're trying to move on here. So for our third example, it says a rectangle has its 2 lowest corners on the x-axis and its 2 upper corners on the curve y equals 16 minus x squared. For all such rectangles, what are the dimensions of the one that's going to yield the largest area? So there's some rectangle that it claims that it's, oops, I can't even draw a straight line, but that's okay. That its 2 lowest corners are on the x-axis and its 2 upper corners are on the curve y equals 16 minus x squared. Well, if I said to you, what does 16 minus x squared look like, I sincerely hope you guys are saying it's a parabola whose vertex up here is 0, 16. Okay, granted, I just kind of butchered the picture, but we have the general idea. So it's saying that you have your 2 corners. I wish I had a better picture, but it'll have to do on the curve itself, and it goes down to the x-axis like so. So these 2 points right over here, I have no idea what they are, so what I'm going to do is I'm going to call them x comma y, and this over here is going to be negative x comma y. So we are trying to maximize this area, and again, what is this a picture of, my friends? You got it. It's a rectangle. However, if I said to you, what are the dimensions of my rectangle? What is the distance from here all the way to here, even though I semi-butchered this, but it's still going to get the job done. If you're going from here to here, I hope you recognize that this is going to be 2x, because from here to here is x, from here to here is a negative x, but my distance is still an x. So this is an x here, and this is an x here. So that means it's going to be 2x, and I'm going up, and that would be y. So my area is equal to 2xy. Now, that's my, which equation? That's right, it's my primary. Now, my secondary equation is, what is it? Do you see anything where we have y in terms of x? Looky here. Sometimes your secondary is going to be handed to you on a silver platter. Is that not delightful? So that means that my area is equal to 2x times 16 minus x squared. So now I have a function of x. So this is going to become 32x minus 2x cubed. Now, you guys are going to be the ones to find out what this is, and you're going to bring your answer to class. Okay, so bring your solution to class on this one. Okay, that's the first thing you're going to do. And then on number 2, you guys are going to do page, hold that thought, just one problem, don't worry, it's only one. In section 3.7, which is our optimization section, you guys are going to be responsible for doing number, oh, I'm running out of time here, this is fantastic, I feel like I'm on a hunt. All right, you guys are going to do number 18 and, number 17. You're going to do page 216. Whoops, come on. Whoops, I'm on the wrong thing. Look at me. You can do page 216. Numbers 17 and 18. And I wish you guys all the best of luck.